more of the ideas behind sort of image analysis and why this contest-based approach can fit very well for a lot of the problems that you're dealing with normally in image processing. And so the things that we'll cover today are really this basic segmentations and discrete binary structures. And so binary just means 1 or 0. So where you just have two different phases you're trying to separate from each other. So to kind of go over the course outline briefly again, we are now here. The next lecture will be then advanced segmentation. So we'll go a little beyond the things we've done today and cover some new ideas with that. And then it moves on to sort of, once you've segmented things, how you can do a meaningful analysis with it, how you can get more sort of metrics out of your images, and then moving beyond single objects to lots of objects, looking at distributions, looking at statistics and dynamic experiments, and scaling up, and then the guest lectures that will come at the end. So as kind of a brief outline, the first is really the motivation. So why is segmentation at all important? Sort of what are the qualitative approaches that we have? How do sort of thresholding, how does this work? And what does this actually mean for us? A little bit on implementation. And then this idea of morphology, contouring, and mask creation. And so those are sort of follow-ups. So once you've come up with a reasonable segmentation, what other tools do you need in order to get good results out of your images? In terms of kind of the applications that we have, simple two-phase materials, so bone, cells, etc. And so when you're looking at a microscopy image, you usually have, something that's the cell and something that's background. And so the two phases you're trying to separate is what's a cell and what's background. With bone, of course, it's a very similar idea. You have something that's bone and something that's air or water or not bone. Then multiple phase materials is sort of the step beyond that. So we'll cover more of that in the next lecture and how you deal with that. So that's where you have, bone with cells inside and air outside, so that you have sort of three different things you're trying to distinguish from each other. Then kind of, filling holes in materials. How do you connect things together? And then sort of looking at more complicated things like segmenting fossils. And that will be one of the things that the exercises today focus a little bit on. So the more challenging ones to kind of play with the data and see how it looks in 3D. And so one of the other cases we'll have is sort of attempting to segment the cortex in the brain. And so this is a CT image of a rat brain and trying to identify a region like this as sort of being the cortex and what techniques you might need for doing that. So again, the literature and useful references. So the books are the same more or less as we had before. These two things are new. And so both of these are quite good presentations that you can look through about sort of models and ROC curves, which is something we'll go into a little bit later. And so this is not coming actually from the area of image processing. It's coming much more from the area of statistics. But these presentations are quite helpful in understanding what the ideas are and why it's so important to use things like this when you're doing tasks. And so that fits quite well also with the Kaggle or the more contest-based approaches to doing image analysis. So if we go back to kind of the motivation of why we do imaging experiments in the first place, you sort of have the very exploratory, where you don't have a hypothesis, you don't have really any or too many assumptions going into it. You just want to sort of see what your samples look like, see what everything's distributed around inside as. And this is kind of the starting point. And so, if you've never looked at a brain before, when you take an MRI of a brain, you're not really trying to prove that you can find Alzheimer's or prove that you can figure out how old a person is. You're just trying to look at the image of the brain and see what might be interesting inside and what some basic differences could be. And so this is where you don't really have any prior knowledge or expectations, and this is also an area where you don't necessarily need a lot of quantitative image analysis. This is something where it is important to just look and maybe label things. What could these different structures be? What might be interesting inside them? Where this, however, shifts away from kind of the qualitative approach is when you start to have a hypothesis that you want to test. And so as scientists, this is where imaging becomes much more interesting, because you want to be able to say, I think, in healthy cells, this flagellum is very long, and in sick cells, this is very short. So you have some sort of clear idea or hypothesis that you want to test, and you want to make measurements in order to sort of confirm or reject your hypothesis. And we'll get into that a bit more in sort of the statistics lecture, but that's really the basic point, and that's where it becomes very important to have more quantitative assessments of things that you're doing. And so, if you have a question for like dynamic material science experiments, does the temperature of the oven that you're producing something in affect the bubble size of the foam that you're looking at? So you have a very clear question, and it requires that you're able to, first of all, find the bubbles, and second of all, measure the size of the bubbles. And so there's a couple of different tasks embedded in there that you want to be able to achieve. The next one would be sort of like a more biological one, where is this gene important for cell shape in the bone? And so you have a gene, you can upregulate it, downregulate it, completely silence it, and you want to be able to see, does the cell shape change as you make those changes to this gene? And then, of course, you have other, from battery life expectancy by the shape of the things inside it, that, the sentence itself doesn't sound very quantitative, but clearly you need to have something you're measuring in order to say that the granule shape affects the battery life expectancy. You have to have some way of saying, this is a shape with a really long lifespan, and this is a shape with a really short one. And if you say, the ones with the long lifespan look like this, and the one with the short lifespan look like that, that's a starting point, but that's still very much in the exploratory area until you can really say it needs to be, have an anisotropy factor of 1.5 or higher. You can't really have a clear hypothesis that you can statistically test easily. And so, when we take an image of a cell, this is what we're actually looking at, where you have sort of all these different organs and all these different features, and you put this through your scanner or your microscope or whatever it might be, and you get out an image like this. And so we talked about that a little bit in the first lecture, that you kind of have this intensity value that corresponds to some physical trait in the image, and you want to be able to do something now with this. And so, we take, from just a pure data perspective, if we have a hypothesis that we're looking at, we want to perform an experiment in bone to see how big the cells are inside of the tissue. And so we sort of take the data, we reconstruct it, we come up with this nice 3D volume. We then go to the stuff that we had from the second lecture, which is, filtering and pre-processing. So how can we, make a Gaussian filter, enhance the features that we're really interested in looking at, and try to repress the noise as much as possible. This can then take a really, really long time, but fundamentally we still have way too much information. We still have exactly as much information as we had before, or data as we had before, and we're not any closer really to testing our hypothesis. That we still have a lot of data, and so how do we reduce this even more to get closer to sort of the goals that we have? And so if we look, what did we want in the first place? Usually it's something like a volume fraction, bone mineral density in the case of bone, the number of cells that you have, how stretched the cells are, the cell volume variability, but ultimately all of the things that we're interested in are single numbers. There might be a collection of single numbers for something like, if you have cells, you want to know what the volume of each cell is, but ultimately you're trying to turn all of this complicated image data into a single number. And so this is a huge amount of compression that you're doing because all you want is one number and you start off with all of this data. And so this is where segmentation becomes very helpful because rather than having all of this image data, we collapse it down into really two phases. So we're still well beyond one number, but we don't have sort of all the different variability that we had before. And so this is where we take everything, kind of break it down into two groups. And one of the important things to mention for this is this idea of Occam's razor, and that the simplest solution is usually the right one. And so if you see techniques where they use, Bayesian neural networks optimized with genetic algorithms and all of these other fancy approaches, you have to question how well all of these approaches are suited to the data set they're applied to, and if it's not overly complicated and potentially introducing new forms of error that are very difficult to measure. So there's clearly problems that require that kind of analysis, but as a starting point, you want to take the simplest analysis that gives you reasonable results, because the more complicated this analysis gets, the sort of further removed you are from your original data and the less able you are to propagate errors forward, which is one of the major issues if you see things like neural networks that if you have something in a self-driving car that's trained to recognize obstacles and it doesn't recognize an obstacle, it is very difficult to figure out why exactly it didn't recognize an obstacle. Whereas if you have a system that uses, LiDAR, like the Google car, where you measure a distance for every point and how far away it is, and you have a simple threshold that says if there's an object that's closer than 2 meters to the car, then the car should brake, that's a very simple system to understand. It's not going to be able to do very, very complicated things like, recognize is this a person or a car or a, bike. But it's very easy for you, as someone who's trying to model the system and determine where it might fail or where the shortcomings might be, to understand what's going on. And when you have very, very complicated systems, it's then very difficult to understand why did it recognize this as an obstacle, but this bar that came over not as an obstacle, and what are the other situations you could have where this system might fail. And that's something that we even saw sort of in the first lecture, that something that identifies an image as a person can be very slightly modified so that it identifies the same image, or almost the very same image, as a jellyfish. And so clearly that's a system that we don't understand particularly well. And so where it fails will often surprise us. And the simpler it is, the easier it is for us to understand where these things might happen. So to kind of briefly review the ideas of filtering enhancement from 2 lectures ago, we basically have this idea where we measure something, and this measurement consists of sort of what we were originally interested in, and then some sort of noise. And if we had a perfect filter or a perfect image enhancement approach, we would sort of apply this to our sample, and it would give us exactly the same information out. And so if you put in a good signal, you get a good value out. It doesn't damage your input signal at all. And when you apply it to noise, it then makes it go to 0. Of course, this isn't really multiplication. You can think of more of as applying it. But that if you take your filter and apply it to your data, you get your sample out and you've removed all of your noise. This is obviously not the case with any of the filters that we're using. And so what we have to hope for is that when we apply a filter that, we only damage maybe 10% of our original signal or our sample and 90% of the things that are noise. Very frequently that's not the case. Very frequently the trade-off is a lot less clear. You throw away a lot of signal in order to get rid of a little bit of noise. But depending on what your goals are, that could be enough. Clearly, for a bad filter, you have something that enhances your noise and completely suppresses your signal. And so if you'll look at some of the ones we covered last time, like Laplacian filters or edge detection, if you have a slightly noisy image and you apply edge detection to it, you will enhance the noise massively, because the noise are the things that change really quickly, and so they look kind of like edges, while you'll kill everything in your image that was a signal. And so that's why with these approaches you have to be very careful on what exactly you're enhancing and what you're throwing away. And so if we look at sort of qualitative metrics, if you have an image like this in your microscope, what did people used to do? And actually, this isn't even used to do. If you go to the hospital today and you have a tissue sample taken out of your body, in most pathology centers in Switzerland, this is then looked at by a physician under a microscope. There isn't any digitalization, there isn't any algorithms that are running on it. It's simply put under a microscope and they put their eye on it and they look for something that looks suspicious. And so, you have something like this and they kind of identify objects by eye where, you count, you describe qualitatively, many little cilia on the surface, or the cell looks like it's very elongated in this direction. And then, if you go back, what did they used to do for kind of morphometric or shape analysis? And what they often did was they would trace an outline of the object and then cut it out and then weigh the cutout that they had made to figure out something like what's the area of the object. Of course, the idea is in this course we're doing much more quantitative analysis that isn't dependent on you cutting something or tracing something accurately. It's based on sort of a set of reproducible image processing steps. So when we kind of look at segmentation approaches, we go back to the worldview that we sort of introduced in the first lecture. And so we kind of have this, experimentalist approach where it's very much model-based, and presumably most of you fit into this category fairly well. So you have some sort of model of the system that you're looking at, and you want to kind of get the image to fit into the model. And so, for the example of bone imaging, that bone absorbs X-rays more heavily than air. And so you use this to try to come up with a set of rules that you can apply to a bone image in order to extract the bone from the air. You also know things that, there probably aren't any free-floating chunks of bone in your body because they would, fall out or go somewhere else. And so if you find something that absorbs more than air, that isn't connected or touching any other bone, then it's probably not really bone. It's probably, noise in your detector or something else. The other approaches, of course, are these deep learning and computer vision approaches. And we sort of group this together as the machine learning approach. And this is where you then don't have an explicit model that you're working with. You're very much focused on the results that you want to get. And so these two approaches are very different because with the first one, you sort of have an understanding for how your system works, and you're trying to optimize it to get the best sort of results out. And with the second approach, you don't presume to understand very much about your system. You simply have some sort of ground truth or gold standard that you want to achieve, and you optimize your algorithmic approaches in order to achieve that. And so we'll cover both of these approaches today and sort of what their differences are and how they sort of work together. So when we take the model-based analysis that we have, you have this idea of some sort of impulse or excitation. You then have your characteristic of interest in the sample, whatever that might be, your response, and your detector. And so, if you look at something like, micro-CT or MRI or atomic force microscopy, you can sort of define what your impulses are, what the characteristics are that you're looking at, and then you can come up with some sort of, I measured equals the transfer function of the system, whatever that is, with the stimulus as one of the inputs and the sample as one of the other inputs. And so basically you're trying to then reconstruct this sample information from whatever measurement data you have. And so if you're working in kind of, the tomography or the computed tomography world, this means the whole reconstruction process, because the things that you measure, aren't really the object itself, but some sort of transformation on that. The same with MRI. And you then have to go back to your original data or your original sample by applying these number of different steps. With things like confocal microscopy, you're actually measuring the sample itself. And so this step is then more about getting rid of background noise and enhancing sort of the features that you're interested in your system. And so when we look at direct imaging, and so this is something like microscopy, where your measurement matches your sample very well, or matches your output very well, you have sort of the F transfer function of your system as being sort of A times B. And so here it's, your beam times your sample, because you have an object that absorbs something that comes through it, and you multiply them together. Obviously, this is somewhat of a simplification of how the system actually works, but if you look at kind of a faraway approach, this works fairly well. You then have your stimulus, which is the profile of your beam, and you have your system, which is sort of this absorption coefficient of your sample. And so if you want to get back to this absorption coefficient, which is then sort of correlated with the electron energy density levels or sort of any number of other parameters based on how you're illuminating it and what exactly you're looking at, then you have this idea where you take your measurement and you sort of divide it by your beam profile. So for computed tomography image, this is just sort of flat field correction, that you take a picture of your beam, you take a picture of your sample in your beam, and then you divide the two in order to get the image of your sample. If you don't know what your beam looks like, there's approaches in microscopy to do things where you then correct or you try to fit a model to the beam because you know it's a Gaussian profile or something like this. If you then look at kind of what a non-uniform beam profile looks like, if you have a gradient like this, and you have a sample that looks like this, then you get something on your detector that has sort of this changing illumination across it. And your goal is to get rid of that changing illumination so that you have an image of just your sample itself. Because if you see some sort of pattern like that, that's probably not inside your sample, and that's probably because something in your system is not aligned or your beam profile isn't flat. Similarly, if you're doing something with laser imaging, where you have a Gaussian sort of beam for your illumination, that you end up with this on your detector, and you need to somehow disentangle that beam profile from this image in order to get the image of your original sample. And that's kind of where that challenge comes in.
Excuse me.
Yeah.
The sample, why is violet? The image of the sample.
Because so the image of the sample here, you don't have to pay too much attention to, because these are all just shown with the same scale bar.
Oh.
So that basically the sample's between 0 and 1, and this shows up as violet because that's sort of the range that's being shown there. But the general idea is that you have these patterns and you're trying to disentangle that pattern from that feature. The color itself is, you can ignore for that. And then for all of these slides, if you go to the course site, I'm not sure if anyone has done this already. It's not in Python for all of the lectures. For some of them it is. But if you go to the old lecture handout, you can then see for all of these figures what the code is behind it. And so if there's something that's kind of unclear, obviously a lot of these tables are quite long and unwieldy. But here, for example, we have this figure that we can see here. This is the code that was used to make that figure in case you had sort of a question about how it got generated. And so all of that is inside there if you're interested in looking through it. It's more for your own reference to kind of see where that came from and to understand something about it potentially in more detail where it's not as evident from the image itself. Obviously, you don't see why that's purple, but you at least have the code so that you could look at the image yourself and tweak things to see if that changed the result. And you have that for all of these graphs that are shown because all of that is embedded in the presentation itself. So none of these images were like made and then copied into the presentation. All of them are actually made as the presentation is being generated. So if we look at kind of absorption imaging, so going sort of one step beyond that, we have this idea of the Beer-Lambert law. So for anyone who's taken the micro-nanotomography course or the elements of microscopy, you should have gone over this law, where you basically have your detector output, and that's equal to the illumination of your source times sort of the exponential of the alpha, so this absorption coefficient, times the thickness of the sample that it's gone through there. And so this is obviously a somewhat simplification because it assumes you have one constant alpha for a thickness. This in reality sort of is more of an integral because you're going through a sample and you're integrating along all the points on a line. And there's obviously wavelength dependence and other things that come in, but that's the basic idea. And so you see with an image like this that you're probing something, like the interaction between the light and the chemical or nuclear structure of the material, depending on the wavelength, and that you have an image of your sample, and that's equal to that source times this alpha coefficient as a function of x and y, and you can then derive what that alpha should be based on what the chemical makeup of your sample is. And so that's where, when you're looking at CT images of something like bone or fossil, you know that because bone has lots of calcium in it, that alpha value will be much, much higher than it would be for organic compounds or air or water, because you can calculate those things for those parameters. And then that gives you the ability to say in your image, if we have an alpha value between 0 and 0.5, then it probably falls into this group. It's probably air, because looking at the different things in air, that's what it should be absorbing. If it's between here and here, it should then be water, because that's what's absorbing in kind of this middle range. And if it's above that, then it's probably bone or mineralized material, because that's absorbing more than we would expect. Then obviously, if you go all the way over here, you're probably looking at something like metal or some much harder compound that is then not bone anymore. And so you come up with these ranges based on what your original physical model is. And so this is sort of the basis for how we do these segmentations. And so by taking your sample and kind of deconstructing what physical properties are you actually interrogating, you can come up with some basic criteria for how you would group things together. And so if we look at kind of what does segmentation do for us, we basically take these decimal values or these image data and we convert it from a floating point or a decimal value into a sort of true or false, a sort of binary output. And so it doesn't really matter what the original value is. It goes ultimately to a true or false. And so, if you're looking at a color image, this then is some rule that takes a red, green, and blue value and turns it into a true or false for a spectrum or a hyperspectral image. It then takes an entire spectrum and turns it into a true or false. And so it really doesn't matter how complex the image data coming in is. It simply takes every point in that data, whatever values are associated with that, and turns it into a binary output. And so yeah, turns it into a single discrete value. And that means that if we go back to our image of bone before, that was 56 gigabytes per sample, because you at any point could have this exact absorption coefficient, you now go down to 1.75 gigabytes per sample. And so this rule massively kind of compresses your data because you're now dividing it into two distinct groups of either it's part of this phase that we're interested in or it's not. So if we now kind of take a very simple image here of a cross, we have this I of x and y, and that's equal to this intensity value that we're showing there. It's between 0 and 1.25, and we make a histogram of this image. And so basically what that shows us is the intensity values that are possible in the image on the x-axis and the number of pixels that are that intensity on the y-axis. And so what this really gives us is the ability to see that these, there are a large number of fairly dark values, so somewhere below, 0.75, and then there's a fairly reasonable minority of pixels that are above this 0.75 value. And so this image we look at and we can see, our eyes can tell that there's sort of two different phases there. There's a cross in the middle, and then there's everything else outside. But what this probability density function tells us is that to distinguish between these two groups is actually fairly straightforward. That we can see if you divide there, you're separating two groups. And so when we talk about thresholds, what threshold means is that you really drop a line somewhere on this histogram, and you say everything below this line is part of group 1 and everything above this line is part of group 2. And so we can then apply that to this image, so this very, very simple rule where if it's above 0.5 it's this, if it's below 0.5 it's that. And then this classifies our image into these two groups, this false and true, or group 1 or group 2. Yeah?
Should this not be above and below 0.75?
Probably, that's quite easy to check. Thresh value is 0.75. So the slide should be corrected. But yeah, so it's 0.75 that we're looking at there, and that's the cutoff value between these two phases. How you pick this value is something we get into later, but the idea is that you simply have a very basic rule, and you apply that exact same rule to every point in your image. And so as soon as you start to add, you can't have x in this rule anywhere. So you can't have like 0.5x there, otherwise it's not a threshold anymore. It's a more complicated transformation that you're performing. So this is what the basic result looks like for the image. And it's really important that when you see an image and you're trying to threshold it, that the first thing you do is make this histogram to see if these things form kind of two separate groups. Because there's lots of images where you can see a very clear difference. When you look at it, the image we had at the very beginning where you were looking at like the cortex, it's fairly easy for your eyes to see where the boundaries of that cortex are. And obviously if you're a trained neurologist, it's even easier for you to see something like that. But that doesn't necessarily mean a threshold will separate those two phases. And so this lets you know that actually there are two distinct groups, and a simple rule of dropping a line will separate that very well. And so the next examples will show where a simple rule of dropping that line isn't quite as easy for separating those two groups. And so we see that you can apply a lot of different thresholds where you drop the line at different points in your image. And so here, if you drop that at 0.2 or 0.3 or 0.4 or 0.5, how that histogram looks different. So basically you're just shifting that line back and forth that you're using to cut off. And then on this side, how your ultimate image looks different. And so even for this image of a cross, it looks like 0.8 or 0.75 finds that cross very well. But this is just one image that you're looking at. And if you were trying to reliably look at a lot of different images, then maybe 0.8 wouldn't actually be the best value to use. And so that's where it starts to be more of an issue of, do you want to make sure you always get every point that might be in the cross? Or do you want to make sure you never get a point that shouldn't be in the cross? And that's kind of what the major challenge of these sort of segmentation problems are, is how do you decide what you actually want to keep? And when you're looking at more than one image, or when you're looking at a large three-dimensional volume, how do you pick a value for this that makes sense, that really gets the information out that you're interested in? Because we see here, in an ideal world, you would have a bunch of values at 0 and a bunch of values at 1. And then you wouldn't have to pick a threshold. All you would have to really say is that if it's less than 1, it's in the first group, and if it's greater than 1, it's in the second group. But this is never the reality, or very rarely the reality that we have. Most of the time we end up with distributions. And so because this isn't infinitely thin, we have to come up with a point that divides these two things well. And so the wider these are, the more difficult it is to come up with that point, and the more kind of misclassifications we're going to make. That there probably are some points here that may not always get classified. Obviously in this image, because it's so few pixels and it's just one slice, it's fine. But with larger images, with thousands and thousands of pixels, there are going to be things that we misidentify. And it's important to think about what those misidentifications mean and what's actually important to be looking at. So when we go to an image that's more difficult, like segmenting cells, we then have this image where you have a standard microscope image, light is shining through, and the cells are absorbing some of that light. And so a blue spot or a white spot is where there's no cell because there's nothing absorbing the light at all, and a dark spot is where there is a cell. The problem is that that's not the only thing that's absorbing light. There's dust, there's probably fluctuations in your intensity, there's a lot of different factors that need to be accounted for. And so how do you decide what counts as a cell and what counts as background? And so here we see the intensity histogram that we had before, and that's not clearly two peaks. That's just one sort of pretty wide distribution. There's probably a point here where most of the things you're looking at are more cells than background, but there's not a very clear way of saying this is exactly where I would drop the line because that's exactly between the two peaks or something like that. And so this is where we kind of try different threshold values and say, this one's probably too low and this one's probably too high. If you're trying to just identify the single dots that are cells, those are probably over or under classifying the things that you're really interested in looking at. And that here, maybe this value in between is quite good, but there's not really any basis for that in this histogram. And so these are the kinds of challenges that make segmentation very difficult because, if you chose this value and you gave the same data set to your coworker, they would probably choose this value or they might choose that value. And so this makes the whole analysis you do quite difficult to reproduce because someone else might look at your data and make a different decision because it's not entirely obvious where this choice would be made. So I think we'll take a break there. And are there any questions on sort of this first part? Yeah?
How do you validate the threshold value, or do you never do?
Oh, that's what we'll do in the next part. Yeah, so we'll go into sort of what approaches we have for doing this better and kind of how we come up with nice metrics for quantifying all of the stuff that I said is important before. So right now it was just important for me to mention these things so that you can think about it a little bit and start to see what are the challenges that we're dealing with. And then we'll cover in the second part of the lecture what tools we have for dealing with these challenges. Because if you just get told what the tools are at the very beginning, it's harder to appreciate that there's a problem that these tools are solving. And it just seems like you're learning a bunch of math or, charts for no reason. And this is to kind of justify why you're learning how to do this, because there are lots of problems. I mean, there's millions of problems where you can't easily draw a line and say, this is the perfect threshold. And particularly when you're looking at noisy scientific experiments, trying to find that line is very, very difficult. So, okay, so we'll take a short break and then continue with the second part in 5 or 10 minutes.